Crack open a Zima and put in the VHS of the XFL, brah. It's time to talk about the extreme value theorem. Well, before we can talk about the really amusingly named extreme value theorem, we're going to talk about this little result first. Suppose f of x is a continuous function on a compact set A. Then f is bounded on A. In other words, its range is bounded on A. Now remember that a compact set in the real numbers is closed and bounded. Yeah, so I mean a continuous function has this property that limits commute with the function, right? So if it's unbounded, you're going to end up with a problem. And honestly, it's not much more trickier than that. So suppose to the contrary that f of x is unbounded on A. It's either unbounded above or below. We're going to go ahead and assume it's unbounded above. So if a function is unbounded above, there is no upper bound, meaning every natural number fails to be an upper bound. So for every natural number, some point in the set has the property that f of xn is bigger than n. N is not an upper bound on the range, so something in the domain evaluates in the range to be bigger than n, and this is true for every n. So here is what's going on. We've got a compact set. I'm just going to draw it as a compact interval, but it doesn't really matter. We'll see that in a second. Every time I draw n equals 1 or 2 or 3 and so forth, 1 is not an upper bound. So there is somewhere down in the domain an x1 so that f of x1 is bigger than 1. Then there's an x2 so that f of x2 is bigger than 2. And it might be bigger than 3 as well. I don't really care as long as it's bigger than 2. And then there's an x3 so that f of x3 is bigger than 3. There's an x4 so that f of x4 is bigger than 4, and so forth. This sequence down here doesn't have to be increasing or anything. It's just a bunch of points. But each x sub n has the property that, first of all, it's in A. It's in our compact set, but also f of xn is bigger than n. So xn is a sequence drawn from the set A, but A was compact, meaning it's bounded. So therefore the sequence must also be bounded, and by Bolzano-Weierstrass, there must be a subsequence that converges and has some sort of limit x prime. But A was not just a bounded set, it's also a closed set, meaning it has all of its limit points. So the xn's are points in A, the xn's converge to x prime. Since A contains all of its limit points and all the xn's were in A, it must also contain x prime. So x prime is in A, and now we're going to use the fact that f is continuous on A and therefore continuous at x prime. We really need to exploit the fact that A contains all its limit points and is continuous at every point in the set. So x prime is the limit point of xn. xn's are in A, therefore x prime is in A. And f is continuous on A, therefore x is continuous at x prime. Which means f of xn was bigger than n. In other words, the sequence f of xn is bigger than 1, then it's bigger than 2, then it's bigger than 3, then it's bigger than 4, and so forth. That's got to go to infinity, which means any subsequence of it also goes to infinity. In other words, f of x sub a sub n goes to infinity. But because f is continuous at x prime, you can commute the function with the limit. So f of x prime is the limit of f of x sub a sub n, which is the limit of f of xn because it's a subsequence of the original f of xn, and that went to infinity. So f of x prime would have to equal infinity, but f was a real valued function. F of any number has to be a real number, not infinity. So we've got our contradiction. Finally, we get to the extreme value theorem. Suppose f is continuous on the compact set A, then there exist 2 points, C1 and C2, which are in the set A, so that for any point in AX, we have f of x is in between f of C1 and f of C2. We did already show the range is bounded, that's true. Indeed, we're not just saying there's upper and lower bounds on the range. We're saying that there is an upper bound on the range, which is in the range itself. There's an f of something which acts as an upper bound, not just some real number that acts as an upper bound. and there's an f of c1 that acts as a lower bound, not just some arbitrary real number. In other words, we can find a maximum and a minimum, not just an upper and lower bound. Every point in the range is less than or equal to f of c2, and f of c2 is also in the range. So it's not just an upper bound, but it's in the range and is therefore the maximum value of the range. And similarly, f of c1 is the minimum. Now, to be honest, we're only going to prove the maximum value f of c2 exists. The minimum is really the same proof. We're just not going to do both. So we start by saying f is continuous on the compact set A and is therefore bounded. Now, if it's bounded, it has a supremum. The range of f has a supremum. I'm going to let alpha be that supremum. Okay, so f of anything in A must be less than or equal to alpha. If there is a point where f of c2 is equal to alpha, then yeah, alpha is the supremum, alpha equals f of c2. Nothing can be bigger than the supremum, so nothing can be bigger than f of c2, but some point in the domain, specifically c2 itself, evaluates to f of c2. Therefore, we found our maximum. So if there is some point, which we're calling c2, where f of c2 equals the supremum of the range, then we're done. So f is bounded, it's got supremum alpha. Now the supremum isn't just an upper bound, it's the smallest upper bound, meaning alpha minus 1 over n is not an upper bound. Which means alpha minus 1 over n not being an upper bound, therefore there is some point, and we're going to call it x sub n, where f of x sub n is bigger than alpha minus 1 over n, because alpha minus 1 over n is not an upper bound. Some point in the domain evaluates to be larger than it. But since alpha is the supremum, that's what we call the supremum, f of xn can't be bigger than alpha. So f of xn is less than or equal to alpha. So for every n, we can find a point xn where this inequality is true. F of xn is less than or equal to alpha because that was the supremum. But since alpha minus 1 over n is not an upper bound, some point, and we call it xn, satisfies this right here. So the f of xn's, by the squeeze law, have to converge to alpha. Good, that is an important observation. But more to the point, any subsequence of them as well will converge to alpha. Because f of xn converges to alpha, f of any subsequence of xn must converge to alpha. Now, why would I bring up subsequences? Okay, we do know that f of xn goes to alpha. Okay. So now what we have to do, we know that we have a compact set, and again, I'm just going to draw it as a compact interval. It could be any other compact set. This is just the easiest to draw. I've got a continuous function. I'll draw it like this. Okay. What we know is there's some point, which is the supremum, but anything less than it, like alpha minus 1, alpha minus 1/2, etc., is not an upper bound. Specifically, I can find a point x sub 1 where f of x1 is bigger than alpha minus 1. And I can find a point x2 where f of x2 is bigger than alpha minus 1/2. And I can keep doing this. Okay, so the f of xn's must be converging to alpha. However, this picture wasn't necessarily the best idea because I really have no idea where these points are. x1, x2 are right there, but maybe x3 is all the way over here. If the picture went up kind of like this, maybe I could find an x sub 3 so that f of x3 was bigger than alpha minus 1/3, but it was way the heck over there. I really don't know much about the sequence x sub n. What I do know is that f of x sub n converges to alpha. But A is bounded because A is compact. Therefore, the sequence xn, while I don't know much about it, I know it's bounded. And by Bolzano-Weierstrass, there is a convergent subsequence converging to a point, and because the set was compact, it contains its limit points, and therefore the point it's converging to, which again I'm calling x prime, must be in the set A. So since f of x sub a sub n is a subsequence of f of xn, and f of xn was converging to alpha, f of x sub a sub n is also converging to alpha. So now we have two things, a sequence converging to x prime in the domain, x sub a sub n, but the corresponding sequence in the range f of x sub a sub n is converging to alpha. Since f is continuous, I can commute those limit operators. and see that f of x prime must be that limit. But we know that limit is alpha. So there is a point, x prime, which is in A because A contains all its limit points, where f of x prime is equal to alpha, and therefore we're done. We found a point where the function evaluates to the supremum of its range. But reflect, we used compactness very explicitly. We used boundedness of A because we needed to apply Bolzano-Weierstrass. We needed to know that the set was bounded, therefore the sequence xn was bounded, therefore had a convergent subsequence. And we used the fact that A was closed because the sequence x sub n being bounded, Bolzano-Weierstrass gave us a converging subsequence, x sub a sub n. Closed gave us that the limit of the sequence is in A as well. So we needed both closed and bounded. We really needed compactness of A. Now, we phrased this in terms of compactness. We kind of proved it using closed and bounded properties, but the actual statement of the theorem just had to do with compactness, which suggests that maybe you can just construct a complete proof in terms of that original definition of compactness about open covers having finite subcovers. And you can. Okay, but in our context in the real numbers, we know that compact sets are equivalent to closed and bounded sets. So I felt free to use closed and bounded because we're really only looking at the real numbers. As long as we're not focused on compactness in terms of topological definitions, however, we can restate the extreme value theorem in the following way. If f is continuous on the closed bounded set, which we might as well assume to be an interval from A to B, then f has a maximum and a minimum value, which are achieved at points in the interval. This is a typical way you'll see it phrased in books. So why didn't we just phrase it like that? Because you don't actually have to. The general version of the theorem is true. Any continuous function on any compact set has a maximum and a minimum. So why would we bother stating that? Well, if you're not just dealing with the real numbers, you might be dealing, for example, with the plane R2 or real space R3. In multivariable calculus, you still have this result that continuous functions on compact sets have maxes and mins, and even spaces that aren't real. As long as you have this topological notion of compactness, you still get this theorem, which is really quite neat. Now here's a nice useful result. It's not the most amazing result, but we're going to rely on it at a very important point later in the course. Suppose f is continuous on a compact set A, x is a point in A. I define a bunch of sets. For any positive epsilon, I define A sub epsilon to be all the points in A whose distance to x is less than or equal to epsilon. So I claim each A sub epsilon is compact. Here's a brief explanation as to why, although it's not really a full proof. A sub epsilon is closed. What's crucial here is that the inequality is not y minus x less than epsilon, it's the absolute value of y minus x is less than or equal to epsilon. This minor distinction ensures that A sub epsilon is a closed set. It contains all its limit points. You should think about that if it's not clear to you. But A sub epsilon is closed. It's also a subset of A because it's points in A that obey a certain inequality. So A sub epsilon is definitely a subset in A. So A sub epsilon is closed, it's a subset of A. A was assumed to be compact, and a while back we proved closed subsets of compact sets are compact. Therefore, A sub epsilon is a closed subset of a compact set, and therefore A sub epsilon is compact. F is continuous on capital A. A sub epsilon is a subset of A. Since F is continuous at every point on A, it's continuous at every point on a subset of A. So F is continuous on A sub epsilon, and A sub epsilon is compact, so by our previous results, F has a max and a min. These are the values in the range, okay, that I'm calling capital M of epsilon. That is the maximum value in the range of F on the compact set A sub epsilon. And little m of epsilon is the minimum value in the range of F on the compact set A sub epsilon. What we're claiming is as follows. As epsilon goes to 0, this max value, capital M, and this min value, little m, also converge to f of x. Here is a picture indicating what we're kind of attempting to prove here. I'm going to draw a big crazy function here, but it is basically continuous. Now, here is going to be our desired point x. As soon as I define all points epsilon away from x, we have a minimum value and a maximum value. And as I've drawn it, it happens to be the left and right endpoint, but it really doesn't have to be. If I had drawn it, for example, here, and epsilon was really quite large, like this, then the maximum would have actually been here. And the minimum looks like it would have been, actually it'd be over here at the right endpoint. So I don't really know at what endpoint they occur, or if they don't occur at an endpoint at all, but the max and min occurs somewhere in this interval. Now, if I squeeze this interval down, I make epsilon smaller, the max and the min might move. But as epsilon approaches 0, this interval squeezes down to just being at x. The max and the min are going to have limit point f of x, this height right here. That's what we're attempting to prove. All right, so back to the formal proof. Each a sub epsilon is closed, as mentioned, of the compact set, therefore compact, so it's got a max and min. In other words, this m, capital M, and little m, they exist. We don't have to worry about that. Suppose, for the sake of argument, epsilon 1 is smaller than epsilon 2. They're both positive. Then all points epsilon 1 away is a subset of all points epsilon 2 away. If I'm epsilon 1 and that's really small, distance away from x, then I am still epsilon 2, which is slightly bigger away from x. Therefore, the max on that set can't actually be any bigger than the max on the larger set. This is related to old results about supremums on subsets being less than or equal to supremums on bigger sets. Maxes on subsets are less than or equal to maxes on bigger sets. So since a sub epsilon 1 is a subset of a sub epsilon 2, the max on a sub epsilon 1 is less than or equal to the max on a sub epsilon 2. In other words, as epsilon gets smaller, these maxes get smaller. So the max function is monotone decreasing. As epsilon is getting smaller, the max function is also getting smaller, and we've already shown that monotone functions have limits as long as you're taking one-sided limits, and we're only letting epsilon approach 0 from above. So whatever the limit as epsilon approaches 0 from above of capital M of epsilon is, call that L. We want to prove that that L is f of x. Let's assume to the contrary that it isn't. So instead of letting epsilon be totally arbitrary, let's take a sequence of epsilons. 1 over n, a half, a third, a quarter, etc. We can find points in a sub epsilon where the max is achieved. Remember, the extreme value theorem doesn't just tell us that the range is bounded, but that there's actually a maximum that is in the range. In other words, these max values are equal to f of something. So for each epsilon equals 1 over n, I'm going to let x sub n be the point where the maximum is achieved. F of x sub n is equal to the maximum on all points distance 1 over n away from x. Now x sub n's have to converge to L. This is really by definition, okay? So the m's have a limit. The capital M function is monotone decreasing and therefore has a limit. So as x sub n, as n goes to infinity, f of x sub n, which are these maximums, has that limit. But the x sub n's are converging to x because the distance away from x is bounded by 1 over n. Remember, x sub n is some point whose distance from x is less than 1 over n. So as n goes to infinity, the x sub n's are converging to x. But the f of x sub n's are converging to L, whatever that limit is. But f is continuous, so if the x sub n's are converging to x, the f of x sub n's must be converging to f of x. So this shows us that the limit as epsilon approaches 0 from above of capital M of epsilon must be f of x. You can repeat basically the same argument to get the limit as epsilon approaches 0 from above of little m of epsilon, these minimum values, must also be f of x. The only thing that changes, by the way, is that the minimum value function is not decreasing as epsilon gets smaller, it's increasing. Much of the proof remains the same, but up here at the top, the minimum value function is monotone increasing as epsilon gets smaller. But that's still a monotone function and everything else remains exactly the same. So if we look at compact intervals, squeezing down on x, the max-min converges to f of x. That's the gist, okay? We're squeezing down little intervals on a point and asking what's the biggest or smallest we can be. If the distance from x is shrinking to 0, the max and min must be approaching f of x as well. This is slightly more general, not a whole lot more. Rather than just being intervals shrinking down to x, it's any subset of compact sets A. It's not a big distinction for us in this course, but it's a little more useful in general contexts. That's what we're going to call it for now. That last result, sitting in the background, we're not going to use it until almost the end of the class. But in general, the extreme value theorem, very handy to know. Maxes and mins occur for functions on compact sets.